Okay, problem 1, homework 9. So problem 1, homework 9 gives us this stochastic process, and they tell us about the random variable theta and n1 of t and n2 of t. So n1 of t and n2 of t are wide sense stationary. n1, n2, and theta are all independent, and we are also told that theta is uniformly distributed. So this is what the probability density function of theta looks like. I just drew it here for reference. Part A asks us to find the expected value of z of t. So we just take the expected value of this side, the expected value of this side. And because it's expected value, I can separate it into expected value of this minus expected value of this. So expected value of z of t is equal to expected value of n1 of t cosine omega ct plus theta minus expected value of n2 t sine omega ct plus theta. Now, because this is independent of theta and this is independent of n1, I could separate these two guys. And the same thing here. So I could write expected value of n1 of t times the expected value of cosine of omega ct plus theta minus expected value of n2t times expected value of sine omega ct plus theta. These guys, because they're wide sense stationary, are constant. So I'm going to call this guy, call it eta 1. I'll call that eta 2. So we can write eta 1 times this. Well, what's this? This is the integral of this guy, d theta, times probability density function of theta, which is just 1 over 2 pi. So it's cosine omega ct plus theta over 2 pi d theta integrated between 0 and 2 pi. It's a sinusoid integrated over 0 to 2 pi. This goes to 0. Similarly, in the second term, we have eta 2 integral 0 to 2 pi of sine omega ct plus theta over 2 pi, same reason, d theta, and this also goes to 0 for the same reason. So in the end, we get that the expected value of zt is equal to 0. That's part A. Part B wants us to find rz of t1, t2. So they want rz, t1, t2. And that's going to be equal to expected value of z of t1 times z of t2. This is going to be expected value of z evaluated at t1 times z evaluated at t2. So, what is that going to be? It's going to be this whole thing at t1 times this whole thing at t2. So we're going to get a quadratic. We're going to get 4 terms. So I'm going to just write the 4 terms down. So we're going to get we're going to get expected value of n1 t1 times cosine omega c t1 plus theta times n1 t2 cosine of omega c t2 plus theta. Now, because we're doing expected values, I could separate them. Minus expected value of n1 t1 n2 t2 cosine omega c t1 plus theta times sine of omega ct2 plus theta minus expected value of N1 T2 N2 T1 sine omega c T1 plus theta cosine omega c T2 plus theta, and plus the fourth term, expected value of N2 T1 N2 T2 sine omega c T1 plus theta times sine omega c T2 plus theta. Alright, because we know that N1 is independent from theta and N1, N2, and theta are independent, we can separate this term into expected value of N1 T1, N1 T2 times expected value of the cosines, and you could do the same thing for the other four terms. So we get expected value N1 T1 N1 T2 expected value cosine omega ct1 plus theta times cosine omega ct2 plus theta minus let's just one minus, I'm just writing it so that we know it's minus expected value of N1 T1 N2 T2 expected value cosine omega ct1 plus theta times sine omega c T2 plus theta minus E of N1 T2 N2 T1 sine of omega c T1 plus theta cosine of omega c T2 plus theta. Ah, shoot. I'm going to write the third term again. I meant to separate them and I didn't separate them. Okay. Okay. Ignore this piece of garbage over here. We have expected value. So this is the third term. I messed it up. N1 T2 N2 T1 expected value sine omega ct1 plus theta times cosine omega ct2 plus theta plus now expected value of N2 T1 N2 T2 expected value of sine omega ct1 plus theta times sine omega ct2 plus theta. Okay, so because these are both N1, expected value of these guys depend only on the difference between the time. So this is just going to be R1 of T1 minus T2. Fourth term, same thing, because this is N2 and N2. These two terms are different. We can't do that. But we can do something else. So first, now let's work this out. So we get first term, we can write this piece as R1 of T1 minus T2. Now, this we can use a trigonometric identity to simplify. So this looks like cosine alpha, cosine beta. Well, what's that? I can just take cosine alpha plus beta plus cosine alpha minus beta. That's going to give me, because these cancel, 2 times cosine alpha cosine beta. So I divide by 1/2. So it's 1/2 cosine alpha plus beta plus 1/2 cosine alpha minus beta. Expected value of that is 1/2 expected value of cosine alpha plus beta plus 1/2 cosine, 1/2 expected value of cosine of alpha minus beta. So that's what we get here. So we take the 1/2 out. I'm just going to put a line here because I don't want to get confused. So that's separating this step from this step. But these are still equal. So we take the 1/2 because we have a 1/2, and we're going to get expected value of cosine omega c. This is the sum, alpha plus beta. I'm just going to try to do like this. Okay. Plus e. Now we have the cosine of the difference. So we have cosine of omega c t1 minus t2. And the thetas cancel out. Similarly, for the second term, we can simplify this piece the same way. Minus. Because these two are independent of each other, we can write them as expected value of n1 t1 times expected value of n2 t2. So we have expected value n1 t1 times expected value n2 t2. In this case, we use the sign identity. So to get cosine alpha sine beta, we do this minus this, so that gets rid of these guys. We have a 2 here, and we divide by 2. So it's similar to this. So that's why we have a constant 1/2 in front. And now we are left with expected value of sine of the sum, omega c t1 plus t2, plus, we have our thetas adding, plus expected value of, this should be sine of the difference, so we get t1 minus t2. Oh, I forgot my omega c. And the thetas cancel out. Then we get, oh yeah, this should be a minus. I said that before when I was doing the identity. It should be this minus this to get cosine alpha. This minus this, everything divided by 2 to get cosine alpha sine beta. So yes, this should be a minus. Minus expected value of, again, for the third term, we can separate these two because they're independent into expected value of n1 t2, expected value of n2 t1, and we use a similar trig identity. This time it's going to be sine alpha beta, sine alpha plus beta plus sine alpha minus beta. So we're going to get expected value of sine of omega c t1 plus t2 plus 2 theta plus expected value of sine of omega c, this should be like this, t1 minus t2. So that's the third term. Now the fourth term, as we did for the first term, because these are both n2, we're just going to get r2 of the difference. So we get r2 t1 minus t2 over 2. Now, a similar trig identity to the previous. to get a sine of alpha times sine of beta. We do this minus this, divide by 2. Wait, hold on a second. To get, what do we want? We want sine. Let me just make sure I didn't make a mistake. Sine. Just double check. Sine times sine. Right. So we want to get sine. Where are we here? Sine alpha times sine beta. So we get cosine of alpha minus beta. Right. This minus this, divide by 2. Yes. So we get right. So we get the expected value of cosine of omega c of the difference t1 minus t2, the thetas cancel, plus oh, this should be a minus. Wait a second, this should be a minus. Minus expected value of the sum omega c of t1 plus t2 plus 2 theta. Okay, and then we close this bracket. I think I forgot to close some of these brackets here. This bracket, and this bracket. All right. So now, expected value of this guy, because we have a theta in here, it's a sinusoid over integrated between 0 and 2 pi. This goes to 0. Same thing with this. This goes to 0. This goes to 0. And this goes to 0. I didn't touch these guys because they're not functions of theta. So when I take the expected value of them, they come out as a constant. So what's going to happen? I'm just going to use this as an example. So take the expected value of this, I get integral from 0 to 2 pi of cosine of stuff multiplied by the density function, which is 1 over 2 pi d theta. This is a constant which comes out. The integral just becomes 2 pi. So we get cosine of stuff times 2 pi over 2 pi. It become 1, so I just get the cosine. Same thing happens here. Same thing happens here. And same thing happens here. So, also what I'm going to do from here on, I'm going to call T1 minus T2, I'm going to call that tau. So, we get R1 of tau over 2 times, we just have the cosine omega c t, this should just be tau, minus, now in the beginning we called the expected value of n1t, we just called that eta 1, and we call this guy eta 2. So I'm just going to call them that. So we get, let's see, we get this. Now, because this is 0 here, this is a minus, and this is a minus, so we get a plus. We get eta 1, eta 2 over 2 times sine of omega c tau. Right. Then we get minus, we have this a similar thing. We have eta 1, eta 2, because these guys become eta 1, eta 2 over 2 times, we have a plus, so the minus stays the same. So we get sine of omega c tau plus R2 tau over 2 times cosine omega c tau. This cancels with this. So we have the conclusion that Rz of T1, T2 is equal to R1 tau over 2 cosine omega c tau plus R2 tau over 2 cosine omega c tau. Now, because this is all a function of tau, we see that Rz is just a function of the difference, T1 minus T2. So, knowing that, and from part A that the expected value of z is a constant, we can make the conclusion that z of t is a wide-sense stationary stochastic process. Now, part C, they want us to find what Rz of 0 is. So we plug in 0. This becomes 1. This becomes 1. So we just get R1 of 0 over 2 plus R2 of 0 over 2. And that completes part C and the problem.